Hello everyone. In this lesson, we're going to be learning about the derivative as a function. So first, we talked about the fact that a derivative is just the instantaneous rate of change at a particular point. So looking at our derivatives, if we wanted to look how to graph our derivative, we first have a couple things to consider. If we have the derivative of f of x is equal to 0, where f of x, this is where f of x has a minimum, a maximum, or a point of inflection. So if we were trying to graph this, what this means is that the derivative would be 0 wherever you have, for example, something like this, where it goes from going upward to going downward. So the derivative at this point, if we were to take it, we would have a tangent line that is horizontal. If we were to have it going from downward to upward, again, we would have a derivative that is equal to 0. Or if we had an inflection point, which is to say it looks like it goes flat and then it goes the same direction it was going. So in this case, we also would have a derivative that is equal to 0. So this would be how you would graph having a derivative equal to 0. And we'll use this later on when we look at our derivative rules and tests to check whether we have a maximum, a minimum, or an inflection point. If we have that our derivative is greater than 0, this means that the direction of your graph is that it's increasing. Remember, this is the rate of change of your graph, not the graph itself. So the function in this case right here, if we were looking at this, our function is going up. But if you look at the rate of change, what's happening with this function is that while it is going up, the rate of change is that it's going down. So this means that the rate would be decreasing. And then what's going to happen is we're going to have a certain point where about here, where this kind of goes from decreasing to now suddenly it's increasing. So you can kind of see that if you kind of follow it, this is increasing. So if f prime of x is greater than 0, it means that our rate of change is going up. It's increasing. If our derivative f prime of x is less than 0, this would mean that our rate of speed is decreasing. So in this case, we have this is increasing, this is decreasing, and when it's equal to 0, it's either a minimum, a maximum, or it's an inflection point. So this is really important to think about because when you're thinking about the derivative, again, it's the rate of change of your function. Think of it like you're driving a car. A positive derivative means that you are going forward. A negative derivative means that you are going backwards. If you were looking at the function, a positive function means that you have gone some distance forward. A negative function means that you've gone back some distance. And the second derivative actually tells you about how this rate of change is changing, right? So in this case, let's look at this function here for a second. In this function, this point is negative, meaning that the function is negative at this point, meaning that it is, if you were, again, driving a car, it means like you're back some distance from where you started. Up here, we have that the function is positive, meaning that you are forward some distance. The rate of change is that from this point to this point, you were, in fact, going forward, right? You're going forward, you're still going forward, but like I was talking about with your derivative being the rate of change, is that if we look at this, I was actually talking more about the second derivative, which is the rate of change of the rate of change, which would be that while we are going forward, we're slowing down. And then here, we're continuing to slow down until we get to a certain point, and now we start to speed up. So this is why you have to kind of think about rate of change and the actual position and the rate of change differently. Because again, using the car analogy, function tells you where you're located. Did you go are you forward or are you back from where you started? The derivative tells you the direction that you're progressing, right? So I may be forward a mile, but I'm backing up. Or I may be back 100 feet, but I'm going forward. It's telling me the direction of movement. The second derivative, which for position, the first derivative would be velocity, the second derivative would be acceleration. I can be going 70 miles an hour, but slowing down. Or I could be going 20 miles an hour and speeding up. So if my second derivative was 0, means my rate of change, my velocity, is not changing, meaning I'm maintaining a constant speed. If I have a 0 derivative, it means I'm not moving. It means that while I might be in a forward position from where I started or behind where I started, I am not moving currently. I'm not going forward. I'm not going backwards. So this is why you have to kind of think of the derivative as the rate of change of whatever your original function was. And of course, if you take the second derivative of that, it would be the rate of change of this rate of change. How is this changing? Is it getting higher? Is it getting lower? So now let's talk a little bit about our notation for derivatives. The most common notation we're going to use is the one I used previously, which is going to be this f prime of x. And this means that I'm taking the first derivative. If I was taking the second derivative, in this case, you would add more tick marks for each derivative. So this would be the second derivative, 3 tick marks for the third derivative, and then after that, you kind of start doing a number, right? So you'd say something like the fourth derivative of x, something like this. We also could see the fact that because our function, right, if we start with f of x, is equal to y, you could also write the derivative as y prime. Or the more precise notation we might be used later on, basically, especially if we're doing things with different variables, is we might do something like dy dx. And what this means is I have some function y, and I'm taking the derivative with respect to x. This is the variable that's within my function. Or you might see sometimes something like df dx, so the derivative of this function. Now, this is going to be really important later on, because later on, if we have more than one variable that we're looking at, we may have to specify, for example, if I have the term xy, which has both x and y in it, am I taking the derivative dy dx? Am I taking this derivative with respect to x? Or am I taking this derivative with respect to x? And this is going to be super important later on, again, when we have more than one variable. Your differentiation operators, you might see something like this. We also might sometimes write d dx f of x. And this just would be the same sort of thing as here. So we're taking the derivative with respect to x of some function f of x. You may also, in some books, see a capital D representing the derivative. So it would be d f of x. Or you might see, again, if you want to specify with respect to which variable, you might see d with a little sub x f of x. And these are all ways that we can write derivatives. Now, this is the notation that we use based on the fact that most calculus that we do is based on Leibniz notation. If you were to go further back in time into text, if you were to look at things based on Newton's work, you would actually see completely different notation for when he was dealing with what he called things like fluxions and things like that. So even though, everyone generally says that Newton created calculus, there is some controversy over that, because him and Leibniz kind of co-created it separately at the same time frame. Well, we use this sort of notation because while Newton is kind of given precedence of creating calculus for the most part, this notation is a lot easier for most people to work with, to understand. It's a little bit more precise, and it just works a little better in most cases. Now, going back to what we talked about previously with continuity, if our function f is differentiable at some point a, then it's continuous at a, though continuity does not imply that it's differentiable. So that is to say that if we had something like the function f of x is equal to the absolute value of x, right? We have an absolute value, so if we were to graph this, it would look like this. In this case, this is continuous, right? It has a derivative that is approaching a specific point from the left, the same point if you take the limit from the right, and the point does exist. This is continuous, but it's not differentiable at 0. So if you can take the derivative of some function, it is continuous. But just because a function is continuous does not mean that it's differentiable, because the derivative of this would be equal to, well, it does not exist. So it doesn't equal anything. Does not exist. So let's do an example using our definition of a derivative. So let's say that we have the function f of x equals the square root of x. And we want to find the derivative f prime of x. So first thing we're going to do, we're going to use our definition of a derivative, and we are going to take the limit as h goes to 0, and we're going to use f of x plus h minus f of x divided by h. So just like before, when we were first looking at how we can do this, we have f of x is equal to the square root of x. So what we need now is we need to figure out what is f of x plus h. So if we were to then just plug x plus h into our square root, we would get the square root of x plus h. So now we can find our derivative by taking the derivative of f of x is equal to f of x plus h, which is going to be the square root of x plus h minus f of x, so the square root of x. And then, of course, we're taking the limit as h approaches 0, forgot to write that in, and divided by 0. Now, let's go back to our tricks and rules that we used when solving limits. So in this case, if I were to just plug in h goes to 0, I would get a 0 in the denominator. So we're not going to be able to do that. So just like before, you could try dividing by the highest power of whatever's in the denominator. In this case, though, all you would end up with is square root of x plus h over h minus square root of x over h, and then h over h, this term would go away. You'd be left with the exact same thing. The only thing is basically it's like you split it, which you can do right now. So what we're actually going to do is we're going to multiply by its reciprocal, like we did previously. So I'm going to multiply this by the square root of x plus h plus the square root of x. And of course, anything I do, I have to do it over itself, so it's equal to 1. So this is going to be x plus h plus square root of x. And now that I have this, I can solve this out. So what do we get? We do our first, outer, inner, last. So first, we're going to get that this is equal to the limit as h goes to 0. And then this is going to be square root of x plus h times square root of x plus h. This is going to be x plus h. And then for our inner and outer terms, we're going to get minus square root of x times the square root of x plus h plus the square root of x times square root of x plus h. So those two are going to cancel. And then we're going to have minus square root of x times square root of x. So that's going to get rid of the square root, and it's going to be minus x. And then this is going to be divided by h square root of x plus h plus square root of x. Okay, so now, next step, we have our x, we have a minus x. So now we have h over h times square root of x plus h plus square root of x. Well, our h's can cancel. So then this is going to be the limit as h goes to 0, 1 over the square root of x plus h plus the square root of x. Now, I can plug in this h goes to 0, because if I plug into 0, wherever I have an h, this is going to give me, and remember, I'm evaluating my limit, so the limit goes away now. This is going to be 1 over the square root of x plus 0 plus the square root of x. So square root of x plus 0, just square root of x. We have square root of x plus square root of x means that I'm going to get 1 over 2 square root of x. So I have my derivative. This means that whatever x point I have for this function, f of x, which of course, based on the fact that it's square root, we have that x has to be greater than or equal to 0. So whatever x value we have, that's going to be our a, right? That's the point that we're taking our limit as it approaches. This will be the derivative at that point, 1 over 2 times the square root of that x. So let's say my x value was 4. This would be 1 over 2 times the square root of 4, or 2. So 1 over 2 times 2, or 1/4. So what's happening is that if we were to look at what this looks like, it looks something like this. So what's happening is as we go to the right, our derivative is getting smaller and smaller and smaller as my x increases. And this will be true for our domain that x is greater than or equal to 0. So in this case, we would have that our domain is 0 to infinity. But if you look at our derivative here, what's going to happen if we plug in 0 in for our x? We're going to get 1 over 2 times 0. So we can't actually do x equals 0. So instead, our domain is going to end up becoming 0 to infinity with parentheses, because 0 actually can't be included, because we have to consider now what can be plugged in for our function but also what can be plugged in for our derivative. Now let's do a slightly more complicated example. Let's say that we have the function f of x is equal to 1 minus x divided by 2 plus x. So we have this function and we want to find our derivative. So as always, we're going to be using the fact, I'm going to write it down here, so I'll just continue on with it. We're going to take the limit as h goes to 0, f of x plus h minus f of x divided by h. So we have f of x, right? That's our function that we're given. We need to figure out what f of x plus h is. So f of x plus h is going to be, wherever there's an x, I'm going to plug in x plus h. So this is going to be 1 minus x plus h, which is going to be, I'm going to distribute that minus, so it's going to be minus x minus h, divided by 2 plus x plus h. So this is my f of x plus h. So I'm going to plug these values into this, and we're going to get the limit as h goes to 0, f of x plus h, this is going to be 1 minus x minus h, divided by 2 plus x plus h minus f of x. So we're going to subtract this entire thing. 1 minus x over 2 plus x. All of this divided by h. Now for this case, I have two fractions with different denominators. So what I'm going to do is I'm going to multiply this first fraction by the denominator of the second fraction. For the second fraction, I'm going to multiply it by the denominator of the first fraction to get them in terms of the same denominator. So this is going to end up being the limit as h goes to 0, 1 minus x minus h divided by 2 plus x plus h times, and then of course, remember, I'm actually just multiplying by 1, so this has to be 2 plus x divided by 2 plus x. And then now I'm going to go to my second term, so minus 1 minus x divided by 2 plus x times, and again, I'm going to do the same thing with the denominator from the first fraction. 2 plus x plus h divided by 2 plus x plus h. And then, of course, still all divided by h. So this is going to end up equaling, first of all, now both of these are going to have denominator 2 plus x plus h times 2 plus x. So I'm just going to leave that the way it is for now. I'm just going to put that this is 2 plus x plus h times 2 plus x, and put those in parentheses. So this is going to be the denominator now for the new fraction. It's going to be really big. And we're going to distribute these terms together. So we're going to have 1 times 2, so 2, plus 1 times x, so x, minus 2x, minus x squared, minus 2h, minus xh. And then remember, this is going to be minus this entire thing. So minus, I'm just going to put this in parentheses now so we don't lose track. We'll distribute it after. 1 times 2, so this is going to be 2. 1 plus x plus h minus, so that'd be, in this case, it's going to end up being plus, minus x, 2x minus x squared, and then minus xh. Oops. Minus xh. And then I'm going to distribute this negative just to make this a little bit easier, so we're doing cancellation. So by getting rid of this parentheses, this is going to be minus 2 minus x minus h plus 2x plus x squared plus xh. So we're going to take the limit still as h goes to 0, and this entire thing is still divided by h. So now we're going to see if we can do any cancellation, which we will, because that's the whole reason of multiplying by, getting everything in terms of everything. So this 2 is going to cancel with this minus 2. This x is going to cancel with this minus x. This negative 2x is going to cancel with this 2x. This negative x squared is going to cancel with this positive x squared. This minus xh is going to cancel with this positive xh. And then we have minus 2h minus h. So this is going to end up giving me the limit as h goes to 0 minus 3h divided by 2 plus x plus h times 2 plus x, and then this entire thing divided by h. So as always, what I'm going to do now is I'm going to do fractional division, right? So you're going to do multiplication by the reciprocal, and you can think of this h as h over 1. So this is going to take the term and flip it. So this is like bringing the h up to this term and the 1 up to the top. So I'm going to have an h here and a 1 here. This h will cancel with this h, and I'm left with the limit as h goes to 0 minus 3 divided by, and then this whole thing, 2 plus x plus h times 2 plus x. So at this point, I can actually evaluate my limit by plugging in h goes to 0. So in this case, if we do this, this term is going to go to 0. And now that I've evaluated my limit, I don't have to include the limit anymore. This is going to be minus 3 over 2 plus x times 2 plus x, which is just going to be minus 3 over 2 plus x squared. And as other times we took the derivative, this means that as my x from my original function changes, this is going to change what the derivative is in this case. For our next example, let's say that we have the function f of x equals x squared minus x. So if we were to graph this, it would look something like this. Okay, I'm going to create my Cartesian plane, and I know that it's going to cross at -1 and +1, and it's going to look something like this. And the reason I know this is because if I took the derivative, this is the function f of x. The reason I know this is because if I were to plug in 0, I would have 0 minus 0 equals 0. If I were to plug in -1, I would get -1 squared is 1. I get 1, so that would be plus 1. So I know it's going to cross at 0 here, here, and here. Now what I want to do is I want to graph the derivative function for this. So what we're going to do is we're going to be looking at what is the direction at any given point. And from there, we can write where it's going to be on this graph. So first thing we're going to focus on are these points where it crosses 0, right? Because our derivative is looking at where on the graph, like what direction are we facing, right? So in this case, we have that we are going up at this point, we're going down at this point, and we're going up at this point. So if I were to now consider where is my derivative going to be equal to 0? So my derivative is going up until it reaches this point right here. My derivative is going downward until it reaches this point right here, and then from there it's going up. On your derivative graph, wherever it is going up, that is to say that your f prime of x is greater than 0, it's going to be in the upper 2 quadrants. Wherever your derivative is less than 0 or negative, it's going to be in your lower 2 quadrants. And where it's equal to 0, which would be here and here, this is where it's going to be crossing your x-axis on your derivative graph. So we know that this is going to be between 0 and -1. So let's say that this is -1. We know that it's going to cross in between the two, I think at -1/2 probably, something like that. And we also know that it's going to cross somewhere between 0 and 1. So from there, we just have to look at what side or what direction is it going from this case. Well, in this case, to the left of this, it's in the positive, right? So it's going up. That means that it's going to be somewhere over here. And then once it hits that 0, now suddenly my derivative is negative. So I need to be drawing it in the negative part of our graph until it gets to this point where now it becomes positive. So in order to be in the negative, but to go positive after that, I would have to come back up and cross this point. So my derivative would look something like this. Now, one thing when you're graphing derivatives is it kind of throws people off at first because you have to consider the direction, right? So here, the function is negative. Here, the function is positive. Function is negative, function is positive. For the derivative, it's the direction. Direction is positive, direction is negative, direction is positive. Another thing, though, is whenever you're taking a derivative, every derivative you take, you will have one less curve in your graph, meaning that if I took the derivative of this, because it has 2 points where it goes from positive to negative back to positive. In this case, your derivative is only going to have one from negative to positive. Let's take it one step further. Let's say, what would the second derivative graph be? So I'm going to take the derivative graph of this. Well, again, I'm just going to roughly draw this one. If we consider right now, what's the direction of this graph? It's going negative, meaning that I know that I'm down here until I reach this point where now suddenly the derivative is equal to 0, and now it's positive. So the second derivative graph would look like this. Notice that we went from 2 curves to 1 curve to 0 curve. Each time you take a derivative, you will be losing 1 curve at least from your graph. So if you look at the slide here, you can see an example though of what we just drew by looking at our function graph and then drawing our derivative graph based on that function. Now we're going to do an example that's really going to kind of set up the next section. Let's say that we have the function f of x is equal to x cubed minus x. And I want to find the derivative of this function. And then I want to find the second derivative of this function. I want to find the third derivative of this function. And then I want to find the fourth derivative of this function. And the reason we're going to do this is because I really want to kind of show that for every derivative you are performing when you do a derivative using calculus, you are actually using the form that we have done so far in this section, right? We're using the form that the derivative of x is equal to the limit as h goes to 0, f of x plus h minus f of x over h. But in the next section, we're going to be learning derivative rules, which is going to make this all significantly easier. So while you do have these rules you'll learn, which will allow you to solve derivatives significantly faster, significantly easier, this is actually what you're doing in the background, right? These rules are just cases of the fact that if you were to do this, these things also will be true. So you're kind of shorthanding it, right? You're using a trick to go much faster. You're doing this in the background, but what you're actually performing is a much more simple and mechanical calculation. So while it's doing this in the background, what you're actually doing is performing a much simpler and mechanical operation when you do this. So as always, first things first, let's figure out what our f of x plus h is. So if f of x is x cubed minus x, my f of x plus h is going to be x plus h cubed minus x. Now what I'm going to do is I'm going to distribute out this cube function. So this is going to be x plus h times x plus h times x plus h, and then minus x. So first thing I'm going to do is I'm going to distribute this term. So this is going to be first, right? So we do first outer, inner, last. This is going to be x squared. Then we do outer plus xh, inner plus xh, and then last, which is going to be plus h squared. So of course, this is still multiplied by x plus h, and we then have minus x. These two terms together are 2x plus 2xh. Now I'm going to do the same thing. I'm going to distribute this, so this x squared times this x is going to be x cubed. X squared times h is going to be plus h, plus now I'm going to use my 2xh. So 2xh times x is going to be 2x squared h. Now 2xh times h is going to be plus 2xh squared. And then h squared times x is going to be plus, I'll just do xh squared. And then h squared plus h is going to be plus h cubed. And then, of course, don't forget my minus x. Now we're going to see if there are any terms that I can bring together. I've got an x cube term, I have an h, and I have an x squared h, I have an xh squared, I have another xh squared, I have an h cubed, and I have an x. So the only terms that look like they can come together are going to be these two. 2xh squared plus xh is going to give me 3xh squared. So now it's time to plug this into this. So let's do it. We have the limit as h goes to 0, f of x plus h. So we're doing this part now. So this is going to be x cubed minus, I'm going to try to put some of my like terms closer together. So this is going to be minus 3x squared h plus 3xh squared. Wait, did I miss one here? I did this. So 3xh squared and then 3x. I forgot to write down a term. I forgot to do, when I was distributing this, I had the x squared times h. I forgot to put the xh squared. So this actually would go also to, or sorry, x squared h. So this would actually go to 3x squared h also. So just, I missed that when I was doing my distribution. It's a little bit easier when you're writing this on paper than on the board. But okay, so we'll continue on though. Plus h cubed minus x minus h, and then minus our f of x term, which is going to be minus x cubed plus x. Cool. So now this is all divided by h, and I'm going to cancel out this negative x with this positive x, and I don't have, where's my x cubed? And then x cubed and minus x cubed. So these are going to cancel out. So I'm left with the limit of negative 3x squared h plus 3x squared h. Sorry, this should be plus. I don't know why I put a negative there. 3x squared h plus 3xh squared plus h cubed minus h over h. Every term in this has an h. So what I'm going to do is I'm going to pull an h out. So this is going to be the limit as h goes to 0, pull an h out. This is going to be now, so we have 3x squared h, this is going to be 3x squared, plus 3xh squared is going to leave me with 3xh, plus h cubed, pull an h out, I get h squared, and then minus h, I am left with minus 1, all divided by h. These will cancel, and I have 3x squared plus 3xh plus h squared minus 1. Now I'm going to evaluate this limit. I'm going to plug in 0 anywhere I have an h. So when I evaluate this, 3xh, so 3x times 0 is going to go to 0. 0 squared is going to go to 0, and I'm going to be left with 3x squared minus 1. So this is the derivative for this function. That's our f prime x. We have that it is 3x squared minus 1. Now we're going to take the second derivative. So we're going to do the same thing. So we have f double prime of x is going to be the limit as h goes to 0, f of x plus h minus f of x divided by h. But now this is our f of x that we're going to be using here. So this is going to be the f of x we plug in here. So let's figure out what f of x plus h is. So f of x plus h, we plug in x plus h wherever we have an x here. So this is going to be 3 times x plus h squared minus 1. This is going to give us we got to do our square first. So 3 times first, which is going to be x squared. Outer inner is going to be plus 2xh, and then last plus h squared, then minus 1. Distribute the 3. This will be equal to 3x squared plus 6xh plus 3h squared minus 1. We're going to take this, we're going to plug this in for our f of x plus h. We're going to take this, plug it in for our f of x, and we're going to do the same operation, figure out what our second derivative is. So this is going to be the limit as h goes to 0, 3x squared plus 6xh plus 3h squared minus 1 minus f of x. So minus 3x squared plus 1. All of this divided by h. So the 3x and the minus 3x cancel with each other. The minus 1 and plus 1 cancel with each other, leaving us the limit as h goes to 0, 6xh plus 3h squared divided by h. So I'm just going to pull an h out while I'm rewriting this. So I'm going to pull h out, and this is going to give me, so 6xh will be 6x plus 3h squared will leave me with 3h. Divided by h, the h's cancel. And now I'm going to evaluate this where h equals 0. Well, if h is equal to 0, this term is going to go to 0. I'm going to be left with 6x. So this is going to be my derivative or my second derivative of this function, that is equal to 6x. And you'll notice each time it's going to get easier. Now let's take the third derivative, which is again going to be the limit as h goes to 0, f of x plus h minus f of x divided by h, where this is now my f of x for the third derivative, right? Because if I think of this as the function, this would be the derivative of that. So this is going to be my f of x, so I got to figure out what my f of x plus h is. Well, this one's actually pretty easy because f of x plus h is just going to be 6 times x plus h, which is equal to 6x plus 6h. So plug it into this, we get 6x plus 6h minus 6x. And of course, we're taking the limit of this as h goes to 0, and this divided by h. The 6x and the minus 6x cancel with each other, and we're left with the limit as h goes to 0, 6h divided by h, which the h's will cancel. So I have the limit as h goes to 0 of 6. Well, if you remember from our limit rules, the limit of a constant is just the constant. So finally, we're going to take the fourth derivative. So if we were to take our limit as h goes to 0, f of x plus h minus f of x divided by h, if this is f of x, and if I were to plug in x plus h anywhere there's an x into this function, what would I get? Well, there is no x. So this means basically that it's going to be 6. So 6 minus 6 is going to be 0 divided by 0. Basically, what's going to happen is you're going to if you were to follow through with the steps for this, you're going to end up getting that we have, here, let me just write it out. F of x plus h is equal to 6. F of x is also equal to 6. So this is going to end up becoming the limit as h goes to 0, 6 minus 6 over h, which is going to be the limit as h goes to 0, 0 over h, which in this case is, as this goes to 0, it's just going to equal to 0, right? Because the derivative of a constant is going to be 0. So now what we've done is we started with this function, xh cubed minus x. We found the derivative, we found the second derivative, we found the third derivative, and we found the fourth derivative. And notice what happened each step of the way. For the first derivative, we got that it went from a cube function to a square function. For the second derivative, it went from a square function to a x to the first power function. The next time we took a derivative, it went to a constant, and the next time it went to 0. So what's happening each time is that our derivative is going to be 1 power less until we get down to 0. So you can continue taking the derivatives. Now in the next section, we are specifically going to be looking at ways that we could calculate this significantly faster. Instead of filling up an entire page of limits, we'll be able to do it in seconds. The last thing I want to talk about before we finish up this section and then move on to the next section on the rules for derivatives, there are a couple examples where we have non-differentiable functions. The first you can see here is when you have these sharp corners. So in this case, we have some function that is coming from the left and it's increasing until it reaches some sharp point, and then it goes decreasing from there. In this case, this would be non-differentiable. This sort of is like our example where we did the absolute value. It had a limit from the left, it had the limit from the right, it was continuous, but we said it was non-differentiable, and that was why, because it had a sharp corner. The second example you can see here is when you have discontinuous functions. That is to say, if you have a jump or missing point at that point, things like that. Derivatives do rely on the fact that your function is continuous. And the third is if you have a vertical tangent. That is to say, if you have some point on your function where you end up having a vertical line where if you were to take the tangent, it would be a vertical line because this would end up being a case where you're dividing by 0 and it causes all sorts of problems. So that's it for this lesson. In the next lesson, though, we're going to learn all about some of our derivative rules, which will make doing derivatives significantly easier and a lot faster. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.